This video is labeled contingency tables. The test that goes with contingency tables is the test of independence. It's another chi-squared test, but in this case we would have multiple rows with our multiple columns. So we're looking at two variables and how they kind of interact with each other with an expected frequency of individuals in each group. The notation for this one is R for number of rows, C for number of columns, a new equation for calculating the expected values for each square in the table, which would be our row total times the column total divided by the grand total. A new way to calculate degrees of freedom, the number of rows minus 1 times the number of columns minus 1. But it's the same equation for the test statistic, and again this is chi-squared. So we're going to compare our observed and expected values and calculate chi-squared from that. For a test of independence, the null hypothesis is that the row and column variables are independent, which means one does not have an effect on the other. The alternative is that they are not independent, which means that one does affect the other. So we're going to go right into an example. The example is using political affiliation data again. But in this case, instead of just looking at the categories, we're going to be looking at age groups and categories of political affiliation. So two variables. And we want to know if perhaps your age or your generation that you're in affects what your political affiliation might be. So we have political affiliation and age as our two variables. The first thing you want to do is check your requirements. We need, they're the same as for the goodness of fit test. So simple random sample, which we have, it tells us random sample in the problem. X is in categories, and that's true. We have categories of age and we have categories of political affiliation. And we need to know if the expected value is greater than 5 for each. And we're not sure of that at the moment, but we can come back and look at it later. With numbers as large as what's in the table, you can be pretty sure that that will be true. If you had numbers that were a little smaller, you might want to calculate some before you continue. The hypotheses, we could say that age does not affect political party affiliation. Which means that they're independent. And for the alternative, we would say that age does affect political party preference. And that would mean that they are dependent variables. And for any test of independence you do, that will be the standard format for your hypotheses. Okay, step 3, calculate our expected frequencies. Okay. Remember, expected frequency equals row total times column total divided by the grand total. And you have to do that for each box in your table. So it's nice sometimes to just make a new table for your expected frequencies. And then you'll have a table of observed frequencies and a table of expected frequencies. And all the numbers will be kind of in the same places. So for ages we have elderly, baby boomers, Generation X, and millennials. And for political parties, we limit it to 3: Democrat, Republican, or Independent. So we need row totals and column totals and a grand total. So we're going to go up to our observed values, which is what's in this table. So observed values from the sample. And we're going to do row totals first. So 34 plus 34 plus 27. So the row total for that row is 95. Then we have 37 plus 24, or 34 plus 27 plus 34. If you add those up, you get 95. 29 plus 24 plus 42 gives you a row total of 95. And 31, 18, and 45 gives you a row total of 94. Column totals, now we're going to go down a column. So 34 plus 34 plus 29 plus 31, you get 128. 34, 27, 24, and 18 adds up to 103. 27, 34, 42, and 45 add up to 148. Okay. Now, I encourage you to do your grand total both ways. Add up your row totals, and if we do that, we get 379. And also add up your column totals and make sure that you get the same number. And in this case we do. If you did not get the same number, that means you made a mistake somewhere and you should go back and check. So it's an easy way to check to make sure your math is right. So these are column totals. And over here we have row totals. And we have our grand total. So now we have all three numbers that we need to calculate each expected value. So for elderly people who affiliate with the Democratic Party, the row total for elderly people is 95. The column total for Democrats is 128. And the grand total is 379. So the expected value in that square of the table is 32.1. Okay, go over to the next one. The elderly row total, 95. Republican column total is 103. And the grand total, 379. You get 25.8 for that square. Elderly row total, 95. Independent column total, 148. Grand total 379, 37.1. Okay. So continuing on with the expected value calculations, we have now in the baby boomers row, the totals 95, column 128, 379. That should be 32.1. And you'll notice that since the row total is the same for baby boomers as it was for elderly, we're getting all the same values for the expected values for this row. So we had 32.1 here, we have 32.1 again. And the row total for the next row, the Generation X, is also the same. So we're going to end up with the same values in this row as well. So I'm not going to write the numbers down for that one. But then when you get to the millennial generation, we have a row total of 94. So now our numbers are going to be different. We have 94 times 128 over 379. And we get 31.7. 94 times 103 over 379 is 25.5. And 94 times 148 divided by 379 is 36.7. So now we have a table of observed frequencies and a table of expected frequencies, and we're going to use those values to calculate chi-squared. So remember, chi-squared is the observed minus the expected squared divided by the expected. So you'll see we have 12 different boxes in the table. We're going to have to do this O minus E squared over E 12 times and add them all together. In your calculator, there is a way to put in these tables as a matrix. So you'd have a matrix of observed values and a matrix of expected values, and then there's a chi-squared test in your calculator that will compare the two. So for your example on the next page, I'm going to do this both ways. I'm going to write it all out the long way first, so that you can see how you do it by hand, and then I'm going to show you how to put these values into matrix in your calculator and do the chi-squared test. So this is the calculation for chi-squared using the equation O minus E squared divided by E for each group, and then add all the groups together. You can pause this to write down all the numbers, or just write it out on your own later if you want to, but you'll see the sum, which is chi-squared, over here is 11.065. And remember, we're going to be doing these problems by using the critical value method. So we need to know a critical value. So in our table for chi-squared, we use the column for alpha is 0.05. Our degrees of freedom is number of rows minus 1 times number of columns minus 1. And there were 4 rows and 3 columns. And that gives us 3 times 2, which is 6. So if we were to look those up in the table, our critical value of chi-squared, you'd get 12.592 from the table. Okay. So I'm just going to save that number for now. We'll make a conclusion down in number 5, just below this. Okay, so again, all of our O's and E's are in these little equations here. So all of this gives you these numbers that I have over here, and then you add them all together to get your chi-squared value of 11.065. Okay. So let's take a look at how to do this on the calculator. Okay, the functions that you're looking for to do this test, we need to put numbers into matrices. The matrix has its here it is. The matrix function is in your x to the negative 1 button, so just do second x to the negative 1 to get to your matrix function. The first thing you need to do is edit your matrices. So we'll just use A and B. Those are the names that are already in the chi-squared test, is A for your observed values and B for your expected values. So as long as you just keep using the matrix A and matrix B, you don't have to learn how to change the names in the chi-squared function. So we're going to edit matrix A, so just hit enter. And then it wants you to know, wants to know how many rows and columns. So rows is the first number. We had 4 rows. And the second number is number of columns, and we had 3 columns. So now you can see you have places to enter the values, and I'm going to put, again, the observed values, the actual answers from the survey, into matrix A. So we had 34, 34, and 27 across the first row. We have 34, 27, 34. For generation X, we had 29, 24, and 42. And for the millennials, we had 31, 18, and 45. So that's matrix A, our observed values. Okay, now that'll get saved in there. So now we can just go back to the matrix function. So second x to the negative 1 for matrix. We're going to go down to matrix B and edit that. And this one also needs to be a 4 by 3 matrix. And here we had 32.1. So again, these are going to be your expected frequencies, the ones that you calculated. So there's all of our expected values. And just check quick to make sure that they're what we had in our table that we wrote down on the previous page. And it looks good. So now our two matrices are all set. And it'll automatically save them. You don't have to do anything. So our next step over here is a chi-squared test in the calculator. So if we go to the Stat menu, over to Tests, chi-squared is toward the bottom, so if you scroll up, you'll get there faster. So there's the chi-squared test. And here's the matrix name. So again, if you just keep using A for observed and B for expected, you don't ever have to change these. And then you can just go down to Calculate and hit Enter. And that's all you need to do. So the chi-squared value is the first number. This P is for p-value. And then it'll tell you your degrees of freedom, which matched what we calculated before. So let's write these down. .08 we'll round up. And the p-value . So now we can make a conclusion. If we were doing this method from up here, the chi-squared that we calculated was 11.065. And you can see that our chi-squared for the test was less, so that's a fail to reject the null hypothesis. Over here we have a p-value to work with. And alpha is 0.05. So our p-value is greater than alpha, which is another fail to reject the null hypothesis. So it doesn't matter which way we do it. You can calculate chi-squared by hand and compare it to the critical value in the table, or you can put your numbers into matrices and have your calculator do the chi-squared and p-value. Either way, we're getting a fail to reject the null hypothesis, so let's write that in a sentence. The null hypothesis was that the variables are independent, so that's what our conclusion should be. And in the context of the problem, we were looking to see if age affects political party affiliation, and if they're independent, that means it does not. So age does not affect political party affiliation. And that's our conclusion in the context of the problem. All right, so again, this was a test of independence using contingency tables. Contingency tables are when you have two variables or categories within the two variables, and comparing observed and expected frequencies for all those categories.